Hello everyone. Let's wait for a few moments and for others to join. Okay, so we are still waiting for a few more people before we start. Okay, so we have more people joining. That's great. Okay. All right, so maybe we can just start, and when others join, they can just join the conversation. So, welcome everyone.
Started the recording.
Yeah. Okay. So I can record it. Yeah, sure. Of course, if you are watching it in YouTube, it will be automatically recorded. But anyway, so we will be discussing tools from geometry. Some of you know some of these tools. These will be useful for the Australian math competition and the Bose Math Olympiad that are coming up. Those of you who are new to this discussion, um, a big hello and shout out to all of them. This is organized by Cheenta.com, and my name is Ashani Dasgupta. So, I'll say a couple of things about the contests that we are training for. The Bose Math Olympiad is starting in August. So, the training session is happening now. It starts in August. And the curriculum involves number theory, geometry, algebra, and combinatorics. Some of you have already attended the research round, which is great because, okay, so, so some of you have already attended the research round. It's kind of similar to the math olympiads all across the world, and it's also very similar to the Google Science Fair or Intel Science Fair. The research round is at least similar to that. Today we are here with the intermediate level training, and it is also relevant for Australian mathematics competition. Now, some of you are already registered for the Australian math competition. This year, Cheenta is officially approved to be registered for to register students for that. We are an official school in that sense. So you can go to cheenta.com and ask for registration. You don't need to be a student of Cheenta to get our help for this registration process. You can simply go there and ask our admin people, and we will be able to help you. Now, about the curriculum of Australian math competition, it's still not this. It's very similar to the curriculum of AMC 8 or UKMT intermediate. This is the intermediate level. A couple of levels are there in the intermediate level. So I'm talking about that. So it's number theory, geometry, algebra, combinatorics. It's the same story over and over again. All of these are modeled after American mathematics competition. So it's not very different from that. So if you're taking a math Olympiad program with Cheenta, You have already faced these topics number of times. In fact, I would suggest you to continuously attend the problem solving sessions which happen 5 days a week if you are not attending them, because it will be very relevant for that. Okay, so let's start with geometry, and in fact we will talk about area and perimeter problems. Now some of you already know this stuff, so it would be a little bit review for you. Some of you don't. For them it's a very nice introduction, I guess. We will not be proving a lot of things because this is an overview session. Let's talk about the area of a rhombus. So what is a rhombus? A rhombus is a quadrilateral, all of whose sides are equal. All the sides of the quadrilateral are equal. So let's say this is A, this is B, this is C, this is D. There is a very nice formula to compute the area of a rhombus, and that is the product that involves the product of the diagonals. So let's see what it is. One of the properties of the diagonals of a rhombus is that if D1 is one diagonal and D2 is another diagonal, then D1 is perpendicular to D2. So how do you show that? Well, that is, I guess, something that you will have to try. So here is a exercise problem. Show that the diagonals of a rhombus are perpendicular to each other. Now, if you look into it, you immediately see that it not only is perpendicular to each other, they will bisect each other. So these two are equal, these two are equal. One thing that kids make a little bit mistake sometimes is that they sometimes think that the diagonals are equal in length, which is definitely not the case for a general rhombus. In fact, if the diagonals are of equal length, we can say something about the rhombus. Can anyone tell me what can we say about the rhombus if the diagonals are equal?
According to me, yes, sir. It's a square.
It's a square, but please raise your hand. Thank you. So if you are new to our classes, uh, raising hands is a useful technique of keeping everything going. So yeah, if the diagonals are equal, so here is an exercise 2 maybe. If the diagonals are equal, then you can show that it is a square. So implies. Okay, that's great. Now, if you can find out the area of triangle ABC from here, which is half of AC times, let's say, BO, because this is perpendicular, BO is perpendicular and AC is the base. Similarly, the area of triangle ADC is half of AC times DO. Again, ADC, AC is the base, DO is the perpendicular. So you can easily add them up to get the area of the rhombus ABCD and get half of AC common, BO plus DO, which is basically half of AC times BD, which is half of the product of the diagonals, D1 times D2. So this is a general formula. Many of you know this, but it's extremely useful for our purpose. It's extremely useful. So that is one part of the story. And some of you, in fact, may remember that we did a problem some times ago on three-dimensional geometry where we found a rhombus inside a rectangular parallelepiped. I will, if you were not there in that class, I will give you an example of a situation where this example is from American Mathematics Competition 8, I think. And it's a very nice example where a rhombus comes up in a very unexpected, or rather a very different type of scenario. So we start with a cube, and we can, as far as I remember, what we did is we took the midpoints of the two opposite sides like this, and we took the diagonals, the diagonally opposite vertices, and we drew these lines. And there is this region that was floating in the air like this in between the rectangular parallelepiped, and we could show that this was a rhombus. So those of you who have not seen this problem, here is the given data. The given data is, this is a cube. Cube means all the sides are equal, of equal length, so it's a cube. And this M and N are midpoints, and are midpoints, and A and B are the endpoints of the diagonal of the cube. So for starters, you can try to show that ANBM is a rhombus. Does anyone remember this problem, and do you remember if this was
Yes,
a square?
I remember we had done it during the classes.
Correct. What was so curious about it? What were we guessing it will be, and it did not happen?
So it would be a square.
We all are guessing that it will be a square, but when we found out the angle was somewhat 65.5, one of the angles, and so we concluded it is not a square, but it is a rhombus.
Yeah, it is not a square, in fact. So it's kind of nice that this happened, and it was an application of the idea of a rhombus. Anyway, so the main job is to show that we have to find the area of this quadrilateral ANBM, and one of the things that we can easily see that it's a rhombus is by checking that this triangle. I'll give you a hint. This MFB, those who are seeing this for the first time, this hint is for them. If you look at this blue triangle, you will immediately recognize that MB is the hypotenuse of this right triangle. So MF is half and FB is 1. So you can immediately compute MB square as 1 by 2 whole square plus 1 square by Pythagoras theorem. So 1 by 4 plus 1, which is 5 over 4. So in fact, MB is square root of 5 by 2. In fact, this same construction will work for AM, because AM is a part of this particular triangle here. It will work for BN, because BN is a part of this particular triangle here. And it will work for AN, because AN is a part of this particular triangle here. It's a very nice problem. You are looking at right triangles everywhere, and the sides of the quadrilateral AMBN appear as the hypotenuse of these right triangles. So once you know that this is a rhombus, you can immediately find out the area of it, because you can compute the length of this particular diagonal AB. You can compute AB, and you can also compute MN, because if you lift MN upward, you will get the diagonal of this top face. Just slide MN upward, and you will be able to see this as a diagonal of this top face, and you know how to compute the length of the diagonal of a face. So I'll leave it to you to complete it. Now there is a similar problem that we will be very interested in. It is the area of a trapezium. Now, area of a trapezium, which is the next idea in the list. Let's see. Yeah. So area of a trapezium is very simple. Okay, so here is a question that Siddhi was asking, that I responded to that question, Siddhi, that how do we know that it is a rhombus? If you are new, you can just look into the previous talk that we had. We discussed why it is a rhombus. Each of the sides can be proved to be equal to square root of 5 over 2. So we proved that each side is equal to square root of 5 over 2. So you can sort of scroll back a little bit and check. Okay. All right. All right. So now the thing is that area of a trapezium is, in a way, it is a funny story about area of a trapezium. In many books, you will see that especially in older books, you will see that area of a trapezium is discussed first in a coordinate geometry book, because there are certain interesting properties of it, and there is a very nice way you can actually compute it. But if we look at it from a modern perspective in a more easier sense, so A, B, C, D is the four vertices. How can we get its angles as square? So Siddhi Berry is asking, let me answer this question from the previous problem. How can we get its angles as squares? So it's not a square, it's a rhombus. And how do you know it's a rhombus? Well, you can compute the diagonals of that quadrilateral, and you will see that one of the diagonals is, I think, square root of 2, the other diagonals is square root of 3, because one of the diagonals is just connecting the two endpoints of the cube, two diagonally endpoints of the cube, and the other diagonal can be thought of as a diagonal of one of the faces. So since the length of the diagonals are different, you can easily see that it's a rhombus. If the length of the diagonals were the same, it would have been a square. Okay, so this is still about the previous problem actually. Okay. Now, yeah, the side FB is given to be 1. Yeah, that's correct. In the previous cube, it was given to be 1. Correct. Okay, now let's look at ABCD, and we are looking at the area of a trapezium. So here we go. We can join AC, and we can simply find out the area of triangle ABC and triangle ADC. So to find out the area of triangle ABC, we drop a perpendicular. And to find out the area of ADC, we drop a perpendicular, and we drop a perpendicular here from C onto the extended AB. So suppose this point is X. So area of triangle ABC is half of AB times CX, because this is the height and this is the base. And the area of triangle ADC is half of BC times AY. So there's something nice about this thing, because CX and AY are equal. You can check that. CX is equal to AY. That is true. Why is that true? Because AB and CD are parallel lines, right? So the distance between parallel lines are equal wherever you measure it. So this CX is equal to H, and AY is also equal to the same number H, because both of them represent the distance between the two parallel lines. So now we can add them again. So triangle ABC plus triangle ADC is equal to half of H times AB plus CD. Okay, so there is a way I remembered this, because this has a very beautiful sort of implication, that area of a rhombus, if you add these two triangles, you get the area of the rhombus ABCD. Area of the rhombus ABCD, rhombus area, is equal to half times sum of parallel sides times the height, or the distance between the parallel sides. Okay. Now, here is a side note. Check out Loney's book on coordinate geometry. is a very ancient sort of a book, but it has a lot of good material in it. There is a book by Loney on coordinate geometry where he actually derives the coordinate geometry formulas for trapezium, for triangle, and so on. That is, if you know the vertices, if you know the coordinates of the vertices, then you can find out the area of the entire quadrilateral. In that, he does a very nice treatment of the area of a trapezium. I don't have time here to discuss it. Maybe in some day I will discuss it in the class. So it's a nice starting point of it. Okay, so now let's go ahead and talk about the next idea, which is the triangular inequality. Really, one of the best tools to make problems is the triangular inequality. So what does the triangular inequality say? Because it's very simple. If you have A, B, C, 3 points, the triangular inequality basically says that AC plus BC, the sum of two sides, is greater than the third side. That's the version 1 of triangular inequality. There is a version 2, which I think is equally important. The difference of two sides is less than the third side. Sum of two sides is greater than the third side, and difference of two sides is less than the third side. There is a standard problem which utilizes this particular property or this particular triangular inequality. But first, I will tell you why the triangular inequality is true. I mean, it's actually nothing but the definition of a straight line. Okay, so Spandan has a raised hand. Go ahead, Spandan. You have an idea?
So, sir, you told that we have to prove that why the triangular inequality will be true, right?
Yeah. What is the argument? Why do you think it is true? Yes, that is correct.
Yeah, sir. So, sir, actually, if I try to construct a triangle with the third side greater than the other two sides, then I will not be able to do it. So, is it the reason?
Why do you think we can't do that? Anyone else has an idea about why? How can we sort of say why triangular inequality is true? Okay, Dhruv has an idea. Maybe let's hear it from Dhruv. Let's hear it from him.
Okay, so we know that AB is the shortest distance between A and B, and
Correct.
AC plus BC is another log, and therefore it must be longer.
Ah, excellent. So basically, the triangular inequality is same as the definition of straight line or straight segment as the shortest path between 2 points. That is, if you want to go from A to B, the shortest path of doing that is along AB, because that's the definition of a straight line. If you go through another point C, like this, then this path will be longer because it's not the shortest path. That's almost by definition it happens. So there is a, okay, I see there are raised hands by Aditya Punatar. Go ahead, Aditya.
No, sir, I just wanted to say the truth.
Okay, got it. So that's great. Now that we understand this, I will go and illustrate a problem from triangular inequality. Maybe some of you have seen this problem, but this gives you a sort of a standard construction. It's a standard sort of an argument when you do triangular inequality. You have a triangle ABC, and the side length of AB is 13, and the side length of AC is 8. My question is, if BC is an integer, how many triangles can we make? So if the length of BC is an integer, it's a positive integer, how many triangles are there with AB is equal to 13, 1, 3, 13, so 1, 3, 13, and AC is equal to 8. So I'll give a little bit time to all of you to think about it. I see some raised hands in the main class, but for others, I'll just let you think a little bit more. It's given that in a triangle ABC, AB is equal to 13 and AC is equal to 8. Think a little bit more. How many such triangles can we make if we know that BC is just an integer? So the raised hands are there. Maybe I can go to someone else. Let's say I'll go to Aryan Das. Let's hear it from Aryan. What do you think, Aryan?
So sir, the triangle it is given that BC is an integer. How many triangles can we make? So basically the question is, just wanted to ask that how many possible values for BC is there so that there is a triangle, because we already have the values of AB and AC.
Correct.
So what we can do is trying to find out the possible values of BC.
Correct.
So first we can see that as we have to make the sum of sides equal, means the sum of two sides should be greater than the third side. What we can do is start from 6 as BC, because 6 plus 8 is 14, that is greater than AB, and it's also holds the second version that the sum of two greater sides will
okay,
be.
so BC must be greater than AB minus AC. Correct.
Yeah, it's
and so BC must be less than AB plus
AC.
Correct. Okay.
So we can start from 6.
Yeah, so because AB minus AC is 13 minus 8, that is 5. And BC is less than AB plus AC, that is 21. So anything
Yes.
between 5 and 21 will work. So
yes.
6, 7, 8, 9, 10 up to 21. Up to 20, sorry, because it's an integer. So 8 to
Yes.
20, 6 to 20, all of them will work. Yes, very good. So 15 is the correct answer of this one. Very nice.
Yes.
So it's a standard way of standard problem that we often face in triangular inequality. There are many beautiful problems of triangular inequality. In fact, if some of you have learned Cauchy-Schwarz inequality or such kind of other inequalities, in some sense, all of them are triangular inequality, just written in a very different way. The geometry of Cauchy-Schwarz inequality, the geometry of Minkowski's inequality, all of them, it's all about the shortest path problem. Whenever you see an inequality and you are thinking how to prove it, one of the strategies that you can use that think about the shortest path in some dimensional space. I cannot discuss it more here, but in an inequality session, maybe I can talk about that. Okay, let's go ahead and talk about the next thing that we have on the list, that is the notion of a triangle. And we want to talk about similar triangles. Most of you know what are similar triangles, and for a reference, I'll just draw it here. So ABC is one triangle, and suppose DEF is another triangle. Let's use the same color actually. DEF is the other triangle, which is sort of the blown up version of the first triangle. So it's nothing different. So this is DEF. I said this yesterday as well, that there are a couple of ways of describing the situation where they are similar to each other. So one way is the equiangular way, that is the two triangles have equal angles, one-to-one one-to-one correspondence. That is, the blue angle is equal to the blue angle, the pink angle is equal to the pink angle, and the red angle is equal to the red angle, something like that. That's one way to talk about one thing must happen that tells us the triangles are similar. This is definition 1, and then there is definition 2, which is basically using the length of sides, the proportionality. So the corresponding sides are proportional. So AB over DE, both of them are opposite to the red angle. That's why we call them corresponding sides. AB and DE, both of them are opposite to the equal angles. So AB over DE, maybe I can write it in red, in fact, because they are opposite to the red angle, is equal to BC over EF is equal to AC over DF. Okay, so this is the second condition that tells us, this is a definition 2, that corresponding sides are proportional. One of the things that we often use is that we use parallel sides to talk about similar triangles. One way to make similar triangles using parallel sides. So you get a triangle ABC and you draw a line that is parallel to one of the sides, like this. Maybe this is E, this is F. You immediately get triangle AEF is similar to triangle ABC. And that's, I mean, you can think about it in a variety of ways. One way to think about it is using the equiangular property. Both of them have the angle A common. These two angles are corresponding angles. If two lines are parallel, then these two lines are parallel. This is a transversal. So these two angles are equal. And similarly, the green angles are also equal. So the small triangle and the big triangle are similar. Okay, that's one way to make it. There is another way. The another popular way, I mean, there are many other ways actually, but the other popular way is to use a circle. If you have a circle like this, something crazy happens. If you draw two chords, any two chords like this, A, B, C, D, then the two triangles here, AMD and CMB, they are similar to each other. See how easily I reduced two similar triangles. In fact, if you know a little bit of circle geometry, you will immediately recognize that these angles are equal and these two angles are vertically opposite. The pink angles are vertically opposite, and you immediately have similar triangles. But one of the things that people miss out, and this is a very, very important part of the entire story of similar triangles, is that you can do this using any pair of chords in a circle. That's why circles are so beautiful. You can just draw two arbitrary chords which are intersecting each other, and boom, you got a similar pair of similar triangles. Okay, so this is another way similar triangles appear. There is another way in which similar triangles appear. You start with the right triangle. This is a very powerful way of constructing similar triangles. You start with a right triangle ABC. Earlier I told you that if you draw a line that is sort of parallel to one of the sides, you get a pair of similar triangles. The big triangle and the big triangle and the small triangle. You get a pair of similar triangles. But in this case, what we will do is we will just drop a perpendicular from B on the third side AC, and you get three similar triangles. It's kind of interesting. So I will hear it from the students again. What are the three similar triangles? All three of them are similar to each other. So let's hear it from Satya Kapoor. Or maybe, okay, that hands up was gone. So let's go to, okay, that's back. Okay, Satya Kapoor, let's hear it from you. What?
Yes. Yeah, can you just repeat the question?
Okay, there are three similar triangles in this picture. ABC is a
Yeah.
right triangle, and can you tell me what are the three similar triangles?
Yeah. DBC,
Okay, DBC,
ABC,
ABC,
yeah, ADD.
ADB. Very nice. So what is your name?
My name is Sachi Kapoor.
Sachi Kapoor. Okay, sorry, I was pronouncing it wrong, but you did a very nice job. Good answer. Okay, Sachi, so you have DBC and ABC and ADB. That's correct. It's a very beautiful picture, actually. This little triangle, and this big triangle, all of them are similar to each other. And I can actually color code the angles. It's kind of useful when you do that. So these two angles are equal. This blue angle is equal to the blue angle. And the red angle here is equal to the red angle here, because both of them are right angles. So
if we again draw perpendicular, then again will this property work?
yeah, of course. That's a very good question, actually. That's a very good question, in fact. If you can keep on doing this, and you can get a spiral of similar triangles. In fact, what I just did gave me how many similar triangles? Can anyone tell me? DM and DN. I drew two perpendiculars, DM and DN. And how many similar triangles are there in this picture? In fact, this can be an Olympiad problem, a little problem, I guess. How many similar triangles have we created when we... Okay, let's hear it from Anushka. Let's hear it from Anushka.
Yes, according to me, there are 7 similar triangles. Those are A and D.
Okay, A N D is similar to what?
NDB.
NDB, yes.
DMB.
DMB, correct.
DMC.
DMC, correct.
DBC.
DBC, that is correct.
ADB.
ADB, that is correct.
And ABC.
And ABC, that is correct. So we have 7 similar triangles in this picture. Wow, this one is nice. In fact, maybe one of you can make a problem out of this property. What if you keep on doing this, and how many similar triangles will you get at the end of the process? If you do it n times, maybe, So maybe you can find a formula. You keep on doing this. You drop perpendiculars. You keep on dropping perpendiculars,
Sir, I think it will be in the form of 2n minus 1.
Well, we have to check.
To the power n minus 1, actually.
You see, I'm just doing it here, and you see this picture is sort of like this. It keeps on sort of moving.
There is infinite.
Yeah, but for a particular number of n, you can always get a finite value.
Correct.
Yeah. So you can get a finite value for a finite n. So yeah, you can think about this.
Sir, I have a question.
Maybe this will be one of the problems. Yes, go ahead.
Sir, how can we tell that the blue angle of B is equal to the angle C?
Sorry?
So how can we tell that the blue angle that you have drawn at B is equal to the angle C?
Oh, how can we tell that? Okay, so let's go ahead and tell that. So clearly, let's go ahead and okay. So let's see how we can say that. So we have. So one of the things that we don't know Okay, maybe I can just clear everything and draw a fresh picture. So what do we know about this picture? So we have A, B, C, and from the point B we drop a perpendicular, let's say D, and all we know is that angle B here is 90 degree, these two are 90 degree. That's what all we know, right? Now one of the things that we know, let's see if I draw this as the red angle, let's call it theta. So we know that this blue angle is 90 minus theta, right? Because in this little triangle BDC, this angle is 90 degree. This green angle right here is 90 degree. So if this red angle is theta, then this must be 90 minus theta. But if this is 90 minus theta, you can now look at the big triangle. In the big triangle, we have a 90 degree. This is 90 minus theta. So what do you think this angle will be? Angle A. That has to be A, right? So this is red, this is theta. Okay, now let us focus again on this smaller triangle ABD. This is 90, this is theta. What should this angle be?
90 minus theta.
So that's 90 minus theta. So now we have, as by simple angle chasing, we found that the blue angle is equal to the blue angle, the red is equal to the red, and the green is of course equal to the green, and we are done.
But so how to tell that green is equal to 90 degree?
That's the construction. We dropped a perpendicular from B from
Okay,
on
yeah.
AC. So
is that the median?
that may not be the median. It's just a perpendicular from B to AC. Okay. All right. So we have a bunch of ideas regarding all of this stuff. Now let's go ahead and talk about the next idea, which is ratio of areas. It's a very important tool that people often use, and one of the things that comes to mind is the ratio of bases theorem. So you have a vertex ABC, and suppose another triangle share the same vertex and the base is on the same line. This is a typical scenario. This base of the two triangles are on the same line. This line is L. So in ABC, what is the area? So the good news is, if you want to drop a perpendicular, let's say if we drop a perpendicular like this, the same perpendicular will be the height from A to each of the bases. So the triangle ABC's area will be half of H times BC. Triangle AXY's area is half of H times XY. So ratio of the areas will be just ratio of the bases. This is a standard tool that we use all the time. Maybe you have seen this before. There is another thing that we would be interested in. How does ratio of areas of similar triangles work? So that's another important piece of mathematics that might be useful. So if you have two triangles, let's say ABC and let's say XYZ, and triangle ABC is similar to triangle XYZ. Suppose that's what we have. Then what we can say is that ABC's area divided by XYZ's area is equal to the squares on the corresponding sides. Ratio of squares on the corresponding sides. So this is one very useful tool that we use all the time. We use all the time. So you can try to sort of prove this. So here is an exercise, maybe prove this, and I'll give you a hint. The hint is you drop a perpendicular from A and X to the respective bases, and you notice that even these two triangles will be similar to each other. So that's easy to see actually, because this is 90° and this is 90° by construction, and angle C and angle Z are equal because they are corresponding sides. I mean, you do the construction on the corresponding sides. So the green is equal to the green, so the remaining angles will be equal. So these two triangles, these two little triangles, the blue ones, they will also be similar to each other. So basically what you can do is you can take the ratio of the heights and say that the ratio of the heights is equal to the ratio of AC by XZ. And now you should be able to finish this proof because it's just one line from here. You have to try. Okay. Okay, enough about ratio of areas. Let's talk about the big thing, big idea in the room, that is the Pythagoras theorem. This is everyone's favorite. Everyone is creating problems using Pythagoras theorem, and all of us know maybe all of us know the standard statement of a Pythagoras theorem. It's if you have a triangle ABC, if this angle B is 90°, then of course AB square plus BC square is equal to AC square. And there are several proofs of Pythagoras theorem since antiquity. One of my favorite proofs is that it uses this construction from the point B, it drops a perpendicular BE, and it uses this construction and the properties of similar triangles to prove this result. It's a very minimalist proof. Okay, Spandan has a raised hand. Go ahead, Spandan. What do you have in mind?
Actually, sir, to say that there are many proofs of the Pythagoras theorem, and one of the proofs which is not the same like this is discussed by you in one of the classes.
Okay. Okay.
This is
Yeah. I think, I mean, I might have discussed some other proof in some other class. Yeah. There are several proofs of it. In fact, it's a very good survey of proofs of Pythagoras theorem. There is a website called Cut the Knot. You can check that website. Maybe I will post it in the link. Cut the Knot. So Cut the Knot, and it's a very beautiful website with a lot of interesting pieces of mathematics. Cut the knot. Here we go. And you can look it up. Actually, there are many such proofs of Pythagoras theorem. Maybe you can invent one as well. Okay, so there are several good things about Pythagoras theorem. It tells you precisely how to compute the third side of a triangle, given the fact that we have AB and AC in right angle to each other. That's a very good thing. But one question I sometimes ask kids, that what if angle ABC is greater than 90°? What can you say about the relationship of AB square plus BC square with AC square? So if you have a triangle like this, maybe ABC, and the angle here, the blue angle here the blue angle was 90°. So we know the Pythagoras theorem works. What if it's an obtuse angle? What would happen? How can you compare this AB square plus BC square with AC square? Okay, another case would be the situation where it is an acute angle like this. So ABC. So the situation where this angle is acute, what can you say about that? So let's hear it from someone who has, okay, Aryan Das has raised hands. Go ahead, Aryan. What do you have in mind?
Sir, so I think for the obtuse angle, AB square plus BC square will be greater than AC square, and it would be the opposite for the acute angle, that AB square plus BC square will be less than AC square.
Do you have a reason in mind?
So, sir, the reason can come from the proof of Pythagoras theorem only. That suppose we do that, and we can we can get that AB square plus BC square will be always greater than AC square. Like, I don't have a reason, but I've heard it.
Okay, so maybe this is a challenge problem for all of you. It's a challenge problem. Using elementary geometry, can you argue what would happen in either of these two situations? And that could give you something called an extended Pythagoras theorem. In fact, it would be great if one of you can investigate how this. So you see, if I look at this quantity AB square plus BC square minus AC square, this quantity, this becomes 0 if this theta is 90 degree, right? Let's call this quantity K. Let's call the value of this quantity K. So this K is equal to 0 if theta is 90 degree. Can you tell me, if I change the value of theta from 90 to say 180 degrees, so I keep on increasing the value of theta, how fast will the value of K change? Like, will it remain 0, or will it change, or what happens? So this is a nice investigation that all of you can do. You see, there is a little bit of unknown mathematics hidden in different parts of the stuff that we already seem to know. So this is a challenge that you can accept and you can try. Okay, let's move on to the last section of today's class. You never know what you will learn when you sort of think about it. So the last section of today's session is related to circles, and we will be talking about locus problems. Now, time and again, I have talked about locus problems. Oops, sorry. I think I missed it.
So what is locus first of all?
Yeah, let's talk about it. What is the meaning of locus? So basically, if I have a point P on the plane, and the point P is moving in a way, the point P is moving in a way such that it satisfies some condition. Let me write that. P is moving in a way such that it satisfies certain conditions. Okay, so if that happens, we can probably guess how the path traced out by P will look like. Maybe it will look like a straight line, maybe it will look like a circle, maybe it will look like an ellipse. It depends, right? So that path traced out by the point P is known as the locus of P. So,
But sir, how to be sure? Like, it depends on the conditions. But sir, if like, how to be sure that it will always be a circle?
it will not be
if
always.
I-
It will not always
Oh.
be a circle. So path traced out by a moving point is known as locus of that point. Okay, so it's a very useful question to ask, that what is locus given the conditions. Okay, Neha has a question. Go ahead.
Yeah, so my question was, is the path being traced by the moving point, is it satisfying any conditions?
Yeah, that should be given in the problem. We have not yet said what the condition is. So in our case, maybe here is a very interesting problem that I encountered in a book called Lines and Curves. It's a very beautiful book from a Russian author called Vasiliev. So there is this ladder which is out there. It's called the ladder AB, which is standing upright. Maybe you have seen this problem. I have discussed it in some classes, I guess. So you look at the midpoint of the ladder M. Now imagine that this ladder is sliding. Imagine this ladder is sliding, and you mark it in different, it's sliding like this. It's sliding along the x-axis, it's sliding along the floor. So it's A prime, B prime. So you mark again the midpoint M prime of this one. Now suppose it has it is slided a little bit more, maybe something like this. A double prime, B double prime. You again mark the midpoint of it, so it's somewhere here maybe. So M double prime. So one of the questions that you might want to understand is, what is the locus of the point M? What is the locus of the point M? One way to think about it is, if you draw all the positions, and if you sort of join the markings of M, what kind of shape will you get? So anyone has an idea how to approach this?
So we might get an arc kind of thing.
Think about it. So this is a very beautiful, so you see, this will actually be a circle, or a quarter of a circle rather, not a circle, a quarter of a circle, because you can join this O and M prime, you can join this, and you can argue that it's always the half of the ladder. So here is the clue for this problem. Join O with M, the midpoint of the ladder. You can show that OM is always half of the length of the ladder. It doesn't matter what is the position of the ladder. It's always half of the length of the ladder. It's kind of beautiful how it works. If you look at a right angle triangle, in fact, you should look at right angle triangles, because each of these positions define a right angle triangle. If you take the midpoint of a right angle triangle and join it from the vertex O, you can check that OM prime is equal to A prime M prime is equal to B prime M prime. This is always true. In fact, if you try to draw a circle with M as the center and OM as the diameter, or as the radius, you will get the circumcircle of this right triangle. So I will leave this to all of you as exercises, because I don't have the luxury of proving these ideas here, but this is definitely something that you should spend your time on. Of course, if you're attending a geometry module in some Math Olympiad program in any organization, I'm pretty sure they will be covering these ideas. Okay, so we will quickly rush through the idea of an angle. And the main thing to remember about angle is that if you take O, A, B, so if you want to know what is the length of this, or what is the value of this angle theta, you have to understand the definition of an angle, that it is the ratio of arc over radius. So one way to describe angle is, of course, using degrees, but another way, which is more fundamentally mathematical in nature, if I may say so, is the notion of arc over radius. The reason that works is because even if you take a smaller triangle, even if you take a smaller circle, For this particular angle, the length of the arc, the length of the radius, they reduce or increase proportionally. So their ratio always remains constant. The length of the arc was large here, the length of the radius was large. When you make the circle smaller, the length of the arc reduced, but the length of the radius also reduced, so their ratio remained the constant. Of course, that requires some proof. Yes, Aryan, you have a question?
Yes, sir. So, sir, I was in a research of these type of problems. So, I came across a term called radian. That radian is related to this radius, and it is told that if angle theta is equal to the arc BA, then it's called a radian. Means it's that type.
Yeah, I mean, this ratio is sometimes called a radian. The value of this ratio is appended by a measurement unit, you can say, called a radian. And if the radius is 1, of course the arc length becomes equal to the radian. That's the scenario. Okay, so we don't have much more time today to do anything else. Of course, maybe you already know that tangent is perpendicular to the radius of a circle. That is a useful fact, and you should look out for that. At the moment, we will stop out here. If you want to register for Australian math competition, of course, you can approach Cheenta. Remember, you don't have to be a student of Cheenta. You can just be an external student. We don't charge anything except that the Mathematical Association of Australia charges something. So we are just sort of facilitating the process. If you are an internal student of Cheenta, however, you have your student admin to help you out with that as well. And of course, you might be also registered for Bose Math Olympiad. Look out for the other training camps that are coming up soon. And keep on doing great mathematics. I will see you whenever I see you next.